Hey guys, this is Eric Olson with Science Centric. Just a quick reminder to hit that subscribe button and also that little notification bell. Otherwise, how else will you know when we've uploaded new content? ESP. So as we get older, it's no secret that our odds of dying go up. We see way more obituaries for 90-year-olds than we do for 20-year-olds, right? But a study in Science earlier this year suggests that something weird is going on. The authors looked at the death records of 4,000 Italians, and they found that when we reach the age of 80, our odds of dying increases less and less with each passing year. If we're lucky enough to make it to 100, those odds hit a ceiling, a plateau, and they don't increase much at all. In other words, somebody who's 110 years old has the same risk of kicking in the bucket as somebody who's 100 years old. So that sounds pretty good, right? I mean, if we make it to very old age, we can assume that our risk of dying this year is about what it was last year. My guest in this episode says, hang on, hold your horses. Saul Newman, a biologist at the Australian National University in Canberra, has 2 papers out this week that take aim at that study looking at 4,000 Italians that came out earlier this year. He says that sloppy science and problems with data collection can create an artificial plateau in mortality. Unfortunately, that's bad news for grandma. So maybe you could just briefly tell me a little bit about yourself and how did you get into the field of study that you're in currently?
Sure. Well, I'm a bit of an oddball because I started out studying anthropology. I actually blew through a sort of a record of 5 different universities in my undergrad.
Wow.
It finished about in the normal time somehow.
Wow, that's amazing.
Yeah. So I obviously have some sort of ADHD.
Now, is that
happily undiagnosed?
Is that because you switched what you were studying, or?
Yeah. Well, I've gone through from anthropology, and the most interesting thing happening in anthropology at the time was genetics. So I got a professor of genetics to, take me on. I did the equivalent of a master's in Australia. It's called an honours thesis, and you can do it in a year if you're a bit mad on research. And then I worked on life history evolution, a bit of life history theory at a medical school called the John Curtin School of Medical Research for my PhD thesis, and that's where I got into this field. Things get even worse on the ADHD spectrum because I then went off and worked for government and industry on wheat genomics. So yeah, and now I've just come back to academia in the last couple of months.
Oh, okay. So yeah, that's pretty great. I mean, you came back and you've already got a paper right out of the gate. That's fantastic.
Yeah. Lucky. It's not not many people do that. But just lucky, I think.
Great. Well, yeah, I'm sure there's talent involved there as well. But yeah.
Hey, don't underestimate dumb luck. It's underrated.
So, I guess a good place to start is to talk about what the normal course of aging is. What happens as an organism, including humans, go through life. What does this do to our risk of dying, and how does that increase as we age?
Sure. So I'll actually start at birth, because there's some quite fascinating things that happen. But essentially, the first day of your life is the most risky, until you get to very old age, and from that sort of high point of mortality, things tail off really rapidly into childhood. And in childhood, your odds of dying sort of flatline at a very low rate. If you look at all of the UK, there's only a couple of hundred deaths during childhood across the entire population. And that's remarkable. I mean, it's a huge achievement. From that sort of flat line, that all-time low during childhood, things start to get worse at puberty. And they never stop getting worse.
And that's
Is it very cheery, right?
that's a function of testosterone, I'm guessing, on some level?
That's an interesting question.
Yeah.
The Americans did a nice natural experiment with testosterone in baseball
Uh-huh.
a few years ago, and if you look at the sort of that pitching aging profile, if you like, or the batting average aging profile, what happens is that the rate at which your athletes decay in performance changes when you take testosterone. When you hit the roids and you have a much later career peak, but then you have a very fast decline. And that's fascinating. It's so, the reason you get, I shouldn't name names, but the reason you get some batters having a high batting average at a much older age is because of this strange effect of sex hormones on aging rates and the pattern of aging.
Right.
But for humans, when puberty kicks in, a lot of things happen, but immediately your odds of dying start to increase. And at first it's sort of quite rapid and non-linear because you have a natural underlying increase in your odds of dying from what are called intrinsic causes. So, your body is decaying and you become more likely to get cancer and heart disease and things over time. But then there's all the teenager stuff, crashing cars, getting hit by buses.
Right.
Yeah.
It's all the Darwin Award winners, or a lot of them tend to come. That tends to come about in the teenage years, I think. Risk-taking behavior and things like that. So that makes sense. I mean, that makes sense on some level. Yeah.
Yeah, and it has a sort of a wonderful little prosaic name called the Accident Hump. And you got to get over the Accident Hump. And about your 30s.
Yeah, that also sounds about right. So yeah.
That's right.
It's when you start listening to your parents again, right?
Yeah. That's right. And your hair becomes slightly more normal, right?
Yes.
So after the Accident Hump, everything, literally seems to run like clockwork, because there's this idea that mortality rates have a doubling time. So it's sort of the opposite of a half-life. So every 9 years or so in the United States, your odds of dying will double.
Wow.
So, my odds of dying today might be, let's just say 1 in a million. In 9 years, they'll double to 2 in a million. In 18 years, they'll double again to 4 in a million. And it'll keep happening, at this regular interval until I die. Which is what I mean when I say that aging is this sort of relentless thing that, gets you in the end.
Yeah.
So the debate we're currently talking about is whether or not that doubling rate ever slows down or stops. So this argument's been raging for 25 years. It's got quite nasty at times. The basic idea is that some people feel, based on data, that once you hit age 80, that doubling rate tends to slow down a bit. And once you get to very old age, it stops. So to put it in the simplest way I can, what they're saying is that once you get to age 80, things get worse, but they get worse at a slower rate. And eventually, things stop getting worse. They don't get better, right? You're still 95. But by the time you get to 100, things aren't worse. And that's this idea of an aging rate plateau or a mortality rate plateau.
So just to summarize, you're saying that you're as you age, your odds of dying increase, and at what age did you say they started doubling?
Well, they actually start doubling around puberty, but it's masked by all those accidents.
Oh, right.
It's sort of hidden underneath the accident hump.
Right. Okay.
Yeah.
So, and then past a certain age, it appears that this sort of, it doesn't actually stop. You're still, your risk of dying is still increasing, but it's leveling off on some level. That's a terrible one.
That's been that's been the argument, that when you get very old, things stop getting worse, and they level off. So your odds of dying they become like Russian roulette. It might stop at 1 in 6, and every year you play Russian roulette, effectively.
Right, right.
Or it's actually often closer to 50-50, apparently. So it's not like things are great.
Yes, yes.
Yeah. If you're laying odds on people dying, every year there's a coin toss or a, sorry for all the gambling analogies, but it's the simplest way to get it across,
Yeah, it's a great way to communicate risk, I think. That makes a lot of sense to people.
Yeah.
Yeah.
So, but this has huge implications because it suggests that if aging stops in old age, the first thing that happens is that human life is open-ended.
Mm-hmm.
So it means that there's no upper limit of human life. You just need to get more people to that point, and they'll live longer and longer and longer and longer. So, if you started out with 100,000 people and they all toss coins to see if they survive each year, there'll be a maximum lifespan. There'll be a person with a record run of coins.
Mm-hmm.
But there's nothing fundamentally stopping someone getting a longer run of coins and living longer. So
Right.
It effectively is saying that there's no upper limit of human life. There's just a sort of a practical maximum.
Right.
The second thing is that aging stops, and if we could understand that, maybe we could, do it earlier or whatever, whatever snake oil is being sold at the particular time.
I guess though that even though your risk of dying, assuming this plateau exists, is sort of leveling off.
Yeah.
I mean, it's still increasing. So I mean, if you're 110 years old, you may have, there's an 80% chance you're going to die, So, I mean, it seems like it's still not sort of pushing down the overall risk that you're going to die.
Well, the overall risk stays flat each year. So there's a constant risk you'll die each year. Of course, that means that, I can say, well, what are the odds I'll live 5 years and then 10 years? And those odds go down as you project out a longer lifespan. If your lifespan depends on a coin toss, obviously you don't last forever.
No.
It's a bit of a strange distinction, but just because there's no limit on human life doesn't mean there's not a maximum, that you reach eventually.
So you have a study or pair of studies out in PLOS Biology this week, and you reference a study from earlier this year that looked at 4,000 Italians, the death records of 4,000 Italians, and they showed this plateau effect from about 80 years old onward. Is that correct?
That's correct.
And your study in PLOS Biology is saying, well, hang on, wait a minute. This could be reproduced in another way. This could just show up as a result of errors in the recording of these deaths. So could you just talk a little bit about your study? Sure.
Well, the first thing is that there are two problems with this study. The first is the errors. The second is that idea that the mortality rate starts to flatten out at age 80 is highly dependent on one choice. The choice of what ages to fit this model over. So you have a single model, you have two inputs to that model.
Okay.
That's it. These authors have taken two very specific inputs and fit what they consider a sort of a best model. The problem is if you change either of those inputs by a single year, the fit of the model gets better, but the size of that deceleration gets smaller. And if you fit all possible combinations, so there are 861 ways you could have fit this model, theirs is the most biased towards their own conclusions. So it generates the largest plateau, but it's also got the worst fit.
I think you may need to unpack that just a little bit.
Sure.
Yeah.
Sure.
Because we're getting into sort of statistics there, and so maybe a little bit of background on.
Sure. So to simplify it, they've made this statement that we have a model, the model fits really badly. Therefore, we need a special late life plateau model. The only problem is the model that they say fits really badly is dependent on their own choices, and their own choices are really biased.
Okay.
Like extremely biased.
I see.
And the simplest way to test this is to take figure 1b, which they've got the data on. You just get a ruler and draw a straight line, and you can fit it straight through all of the middle of those dots. Right? It's really simple. Which means that you can fit a model where this effect just doesn't happen. There's no plateau. Yeah.
So there, when we're modeling a curve statistically, depending on the inputs that we put in, the results can look very different. I mean, this is basically what you're saying. And so they've specifically chosen inputs that are going to produce the result that they're looking for. Is that essentially what you're saying?
That's exactly correct.
Okay.
And they haven't just come close to the result they want. They've picked the single largest result that they could.
And now what are those inputs? What are those starting conditions that they're choosing to get that result? And by the way, for the audience, I mean, that's usually not an indicator of good science when you're picking and choosing the things you want to pay attention to get the result you want. You want to get the most unbiased result that you can. Yeah. That's
right. So there are two inputs here. What you're doing is you're taking those probabilities of dying, and you're drawing a line through them. And you want to draw a line through a bunch of probabilities over a given age range. So you want to say, I want to pick, age 50 to age 80, and I'm going to draw a line through all those dots, or age 70 to age 90, and I'm going to draw a line through all those dots.
Right. And those are going to be spread out over, I mean, you're not going to have your data points line up on a perfect line. Typically it's going to be, they're going to be a cluster.
They're going to be a little bit noisy. So what I'm saying is that you can pick any two ages that seem quite reasonable, starting from just after that accident hump all the way through to age 80. But if you make all those other choices, you get a line that makes their results disappear, except for the very specific ages that they've used.
I see.
Which is a very convenient result if you want to get published in science, but like I said, it's not a very good way to do science.
Now, are these are the ages of 80, between 80 and 105? Is that correct?
Yeah. So those are the ages you want to predict with your line drawn through these dots.
Right.
So if they predict really well, the line will go straight through the middle of all those dots. If they predict really badly, they'll fall above or below. So they've picked a model where the line falls as far above the real probabilities as possible, which makes it look like there's a mortality plateau.
I see.
If you pick an unbiased model, there's nothing. It's like a skewered kebab. All the dots are right on the line.
Okay. Got it. So that's the first problem that you addressed. And then there's this other issue of errors in reporting death records.
Sure.
Yeah.
Yeah. So off the end of that nice straight relationship, there's a little tail, right? The little curve at the end for the last 5 points that looks like it's flattening out. Now, there's an enormous margin of error on those, but that little tail is composed of these 3,000 or so individuals with very old age records.
And this is past the age of 105, is that correct?
That's right.
So very old people.
Yeah. Yeah, that's right. If you make it to 105, you're doing pretty well.
Yeah, I would say.
Yeah. So my real problem with this is that, of course, these records are from at least 105 years ago, right? They're handwritten in a ledger by someone who's received almost no schooling.
Mm-hmm.
Then they're typed into an Excel spreadsheet or whatever, and they're used to create this database. Now, the problem with that is if you take all of the population of Italy and you add typos into their birth certificates, or you add typos into the transcription of handwriting to an Excel spreadsheet, which I don't know if you've ever read other people's handwriting, right? It's pretty easy to make a mistake.
I can't read my own handwriting, so
no, I know, it's impossible. So when you're reading handwriting from 105 years ago, and you can't ask the Italian person who wrote it, was that a 5 or a 9, or like,
right.
Were you drunk? Like you can't do that.
Right.
So it's very simple to generate errors, and I've simulated rare error. I mean, really rare errors, 1 in 10,000 error rate. So for context, in a clinical trial, if you're writing things in an Excel spreadsheet with double entry, your error rate is about 1 in 500. Right, so I'm simulating 1 in 10,000 error rate. And what happens? You make one of those little tails. Right? Purely out of errors.
Yeah.
Now, that method of error generation has been attacked as wildly unreasonable. Which I don't think it's wildly unreasonable to say that I get a 1 in 10,000 errors when I'm writing down someone else's handwriting. I think that's okay.
And that was
I'd be pretty.
That was the author of the paper in Science earlier this year. Yeah, or lead author. Yeah.
I think you could understand why they're pretty defensive about that.
Oh yeah, absolutely.
But the real problem with that is that typos aren't the only way you can generate these errors. There's very simple alternatives. So imagine I'm going to call you. Imagine you're Sicilian, right? Michael. Your name is Michael Corleone. Okay. You live in a small village in Sicily, and your older sister dies at the age of 95. You have the funeral. You bury her on the family farm. Next week, her pension check turns up. Right? So if you don't like the government, or you just like pension checks, you don't have to say anything. Pension check will keep turning up. Now, what does that do? I mean, that means that her birth certificate is real, all her papers are real, and on paper, she's still alive. So she goes from 95 to 96 to 97. Eventually, she reaches 105. If you then realize that you've committed a decade of pension fraud and register her death, right? You've generated a supercentenarian. And if anyone turns up, you are sure going to say, oh, yes, everyone remembers her. She lived past 105, right? You're not going to tell anyone.
Right.
And you can't detect that error by looking at birth certificates. You can't detect it by looking at death certificates. There's absolutely no way that anyone, including the Barbie et al. Team, can pick up those errors. If you have a couple of hundred of those a year, in all of Italy, you've generated these supercentenarian databases, every single one of which is an error. Right? And that's just one scenario. There's plenty of others. I mean, 10% of these people dodged the draft.
Okay.
Right? They went through 2 world wars. I'd be forging papers to hide from the Nazis.
Oh yeah.
Right?
Yeah. That makes a lot of sense. Yes.
Plenty of plausible scenarios where you pretend to be someone else who happens to be older.
Yeah. And there's also people, I think, that just I mean, I've known older people that didn't know their exact birth date. It wasn't recorded, and they just it was around this date, so they don't know for sure.
Yeah. I mean, so I pointed out that literacy is not great in Italy at this time. It doesn't tell you anything about intelligence, but it says a lot about the ability to read your own documents and know how old you are.
Mm-hmm.
Because the literacy test was literally, if you could sign your own name, you were literate.
Right.
So when, 30 or 40% of the population is, air quotes, literate, of course most people don't know how old they are when they're hitting 55. Right?
Mm-hmm.
Yeah.
So what sort of error rate do you need to see this little tail, as you call it, this little drop off in mortality, or drop off in the increase in mortality past the age of 105?
So to generate a little tail, it depends on the size. You can make one with a 1 in 100,000 error rate, right? Tiny error rate.
Uh-huh. Yeah, that's minuscule.
You're talking a couple of cases of identity theft or pension fraud in the entire population. If you want to make one about the size of Barbie et al., you need about a 1 in 4,000 or 5,000 error rate, which, again, is about the 10th of the error rate that you see in clinical trial data.
Yeah.
Right?
Yeah.
So, it's pretty easy to generate these things.
Yeah. And it's, this study in Science we're referring to, there were only 4,000 records. So,
Sure.
This is, not that there's bound to be, some errors in there.
Yeah.
It's not a huge sample, is what I'm saying.
Yeah.
Yeah.
No, it's not. And if you think about, imagine this is the DMV, because you're in North America. Imagine someone said to you the DMV only makes 4,000 errors across 5 years, right? That'd be great. Can you imagine? That's not wildly implausibly high. That's fantastic.
Yeah, no kidding.
Yeah. So, it's not like these are complicated scenarios.
Yeah. So I guess the question is, you've sort of gone after this study. They've rebutted it. Where do we go from here?
Well, that partly depends on the sense of shame that I can impart on these authors as to whether they ever answer another question from me. I don't know, but I'm really looking forward to, on the 10th of January, I'm going to a conference where I'll be presenting in the same session as the lead author. So I get to ask some thorny questions. But apart from embarrassing people, I have no power to do anything about this.
Yeah.
I've never even been given, I got a scholarship to go to this conference. This is the first time I've ever been paid for this kind of thing in any sense.
Mm-hmm.
My laboratory at the moment is this laptop and some coffee. Right. And these people run Max Planck Institutes. They get tens of millions of dollars a year in funding. So I can't force them to listen to me.
Sure.
Apart from, being a iconoclastic madman.
Well, I guess it's like anything with science. It just, the truth sort of wins out in the end, and how often your paper's cited, and those sort of the popularity of your findings, and that'll probably be the case here.
Well, often popularity will trade off against truth, unfortunately. But I do have that idea that yes, we'll win in the end.
Right. Yeah. The truth.
Yes. Yes, the truth will win in the end. That's right. I'm saying this because last year I criticized a Nature paper.
Oh.
That was abysmal. It was just terrible. They committed rounding errors. So they rounded numbers down to 0, and then they turned those zeros into a 1, and then they fit a model to it, and that made them have this result where they say, humans can't live past 125, right? Purely off the basis of these errors. That paper's been cited almost 150 times. I haven't been cited once. So I'm a little cynical, but I'm a bit hopeful.
Why did you choose to do this? Why did you choose to study this? you're doing wheat yields on one hand and you're doing longevity on another. What attracted you to this?
Partly it was someone sending me that original Dong paper and realizing within about 5 minutes that just how bad the standards had become in this field. Just that you would get something, and this seemed to be largely forced through by bullying from a reviewer. It wasn't an editorial mess. It was really a problem at the review level. But that you would have a paper like that published on what seemed to me to be a simple problem of projecting a limit. It was a bit of a shock. And so when this Barbie paper came out, I'd already been working on how to explain these open-ended distributions of the plateau, and essentially it took me less than a week to get this back to Science as a full submission. It took me about 10 minutes to see what they'd done wrong in the paper. It took me a couple of days to code everything, a couple of days to write the paper, and inside a week it was out. And that gives you some idea of, I guess, the time pressures that a lot of scientists have at the moment, that they don't seem to have enough time to really think about what's underneath these models and what assumptions are going on. Because I've got no money and no grad students to take care of, and I've got a bit more time. I have children, but somehow I've been finding the time to think about it.
Well, it sounds like it's low-hanging fruit in a way, and that seems really necessary, that people are checking in on things that are being published and calling it out when it needs to be called out.
I think that it's actually surprisingly rare. So for example, the telomere hypothesis of aging has been kicking around forever.
Oh yeah.
And it doesn't make any sense. And people won't say that.
That's the idea that your telomeres get shorter as you age, right?
Well, that they cause aging.
Okay.
I've got no problem that they get shorter with age. All sorts of things change with age. The problem is this idea that it causes aging. And it was like, if it's that simple, why have we had thousands of papers published on this and not one causal gene experiment? We've got the mechanism. We've got a way of changing these genetic variants. So why do people think this is real? Yeah. I can't answer that. I don't know why.
Sounds good.
Yeah. And you don't want to annoy a Nobel Prize winner, right? Like, if Elizabeth Blackburn writes a healthcare book about it, then
yeah, that's right.
Yeah.
Thanks so much for coming on, Saul. I really appreciate it, and good luck with your future endeavors.
Thank you.
All right, great.
Thanks for having me.
All right, thanks. That's it for this episode. If you enjoyed, don't forget to like and also hit that subscribe button. Thanks for watching, and until next time, I'm Eric Olson.